have something a little different for you today. I have a little bit of history today. There's this mathematical story that's been passed down the generations, and I don't know myself how true it is. I read it from many different sources, but who knows? It could be one of those things that, evolved over time, and I don't know how true it is. But it's fun to think that it's true anyway. The story involves a very respected and famous mathematician named Carl Gauss. I have a picture of the culprit on my computer for you. Well, this is in his older days. Now, Gauss was considered so important that, check this out, in Germany they actually put Gauss on their money. This is a 10 Deutschmark bill. Now, Germany uses the euro now. They don't use Deutschmarks anymore. But when they did, he was on their 10-mark bill. And you probably can't see it there. I'm going to zoom in for you. A close-up there. There's actually a mathematical equation and a mathematical graph on their money. And there's all kinds of fancy symbols there. I was very impressed. Haven't seen that in the US yet. All right, well, so what did Gauss do? Well, the story goes, when he was a kid, 10 years old, in class, his teacher tried to give the class some busy work so that they would, get out of his hair for maybe a half hour or so. And what he told the students they had to do was to add the numbers from 1 to 100 and tell him what the total was. Well, they didn't have calculators then, so I don't even think they had nice pens and paper. I think they were working on slates. And so here they would be, trying to add up the numbers 1 to 100. And if you do it all by hand, one number at a time, it's fairly tedious and would take you quite a while. Well, the story goes, good old Gauss whipped out the answer in like 30 seconds or something and said it was 5,050. So I suppose the teacher was astonished if he didn't know how Gauss actually did it. Well, I'm going to show you how Gauss did it. It was actually very clever, and it leads to a well-known formula, but the idea of a 10-year-old thinking this up, if the story is true, we'll assume it's true because it's more fun that way, right? I'll show you what he did. So on my trusty math cam here, I've started with the numbers we're going to add up, 1, 2, 3, 4, etc. And Gauss, instead of saying, okay, well, let me just start adding these up, what he did was he thought of both the beginning and the end of this sequence of numbers that he was going to add up. So he was thinking about, okay, how's this going to end? And we're going to have 97, 98, 99, and finally at 100, I'll be done. Well, Gauss, as I mentioned, was clever. And what he did was he noticed that if you take the first number and the last number, so if I take 1 and 100, I will get 101. Now take the second number, 2, and the second to last number, 99. If you add those up, guess what you get? Again, you get the same sum. You get 101. What if you take the third number and the third to last number? 101. And it makes sense. The first number is just getting one bigger. The last number is just getting one smaller. So if he pairs them up this way, every pair is going to be 101. So all he had to do was say, okay, how many pairs do I have? Well, if I have the numbers 1 to 100, and I split them into pairs, that means I'm going to cut that total in half. So what he figured out was I have 50 pairs, and each one sums up to 101. So 50 times 101 is 5,050. There, he's done. So all this is an example of a formula that you actually would see in certain math classes, maybe like college algebra class, for instance. And I know in calculus, actually, you use this formula to figure out some bigger problems. The formula says if you add up the numbers 1 plus 2 plus 3, etc., and you end up at some number n, whatever number you like, the total is always the number you ended with times the number that's one larger over 2. And if you look, that's exactly what Gauss ended up using. Now, I don't think Gauss knew that formula. I don't know. It's hard to say with the way the folklore went down, but it's a good story. And in fact, if you look up any history of Gauss at a website or a book, I bet you anything, it's going to mention that story. All right, so a little history for you. There's lots of interesting little stories, and Gauss is just one of them. So maybe in the future we'll pull up some more for you. Some new neighbors that flew in just recently. We have had a friendly invasion of swallows. And these are the same swallows that hit San Juan Capistrano every year. They're called cliff swallows. And they're called cliff swallows because they used to build nests against the edges of cliffs. But it turns out our man-made buildings are especially nice for these guys. So now they come and like to build nests on our buildings. And these nests are made out of mud. They make little pellets of mud, and they assemble these little nests. Now these guys are pretty amazing. They've spent the winter in South America. They seem to like Brazil, Paraguay, and Argentina. But then they like to come back up here in the spring to start laying some eggs and have some kids. So they've actually flown up just last month, and they've flown 7,500 miles in 30 days. Now this is pretty amazing. They fly sun up to sundown straight every day. They don't even stop for lunch. In fact, they eat flying bugs as they go. They don't even stop for that. So sounds tasty, doesn't it? Actually, each bird eats an average of 1,000 bugs a day. Okay, so what we're going to look at is how fast these guys have to go to make all this happen. So a little bit of some average speed computations inspired by our new friends hanging out on our buildings here at Palomar. So first of all, they have to go 7,500 miles in 30 days, roughly speaking. So if you divide that out, it turns out to be 250 miles per day. So what I thought we could do real quick is we're going to figure out how fast these guys have to go on average to make that happen, 250 miles a day. And I mentioned that they actually fly straight from sun up to sundown. So they usually start flying in March. So let's say average, I don't know, let's say a 12-hour day. So let's say they're going to fly 12 hours, 250 miles. How do you figure out what speed they have to maintain to make that happen? And you know, it's actually not too hard if you just think about the units, because we're going to measure how they fly in miles per hour. So over to my math cam for a moment. I'm going to show you a quick little computation we can do and figure out exactly how fast these guys have to go to make this happen. So we said 250 miles, right? So here's 250. And I'm thinking of my units. My units are miles per hour. So just keeping that in mind, if I divide by the number of hours, I should get how fast rather, these guys have to go. And this turns out to be 20.8 roughly. So I shouldn't put equal, we'll say approximately. It's approximately 20.8 there. So to maintain that speed, that's about how fast they have to go. All right, well, average speed is kind of interesting. If you look at what we just did here, all we did was we put the distance that they flew and we divided it by the speed, or you can call that the rate. And that gave us, actually I lied, this is the time, that gave us the rate. So if you think about it, this is measured in miles per hour. This is actually based on that old formula you would learn in any algebra class, this old distance equals rate times time. So all this is distance equals rate times time, a little bit rearranged. So I thought what would be interesting is let's do a sample scenario how you would actually compute average speed, because it's not quite as intuitive as you might think in some cases. But this is the key. You want to keep these distances and times we're going to measure in mind. So let's just do a little scenario. Let's say one of these swallows leaves friendly Argentina and is going to fly up here. And he's on one day of the swallow's flight. He has to fly 250 miles. Let's say, just hypothetical here, let's say for the first half of the trip, the bird flies, I don't know, a little fast. Let's say he goes 25 miles per hour. Let's say for the second half of the trip, he slows down. I don't know, maybe gets a little tired, ate too many bugs, you know, something like that. Let's say he goes 20 miles an hour. What I could ask you then is, what is his average speed for the day? And you know, if you were, I don't know, if it were me just trying to make a guess, I would probably say, well, it's got to be halfway between these two speeds. So yeah, I guess that would be 22.5. I think he's going to fly 22.5 miles per hour average. Well, it turns out that isn't actually quite true. So what we're going to do is we're going to figure out exactly what his average speed was. And what we need to do for that is look at the total time and the total distance, because we want miles per hour. So I know how far he's going to go. It's 250 miles. But let's figure out how long it's going to take him to do these trips. And all we have to do for this, we're going to do a simple little rearrangement of our formula. So we had distance equals rate times time. I'm going to rearrange this just a little bit, and I'm going to solve it for time. So what I want to know is how long will this swallow fly at each of these speeds. So we're going to divide both sides by r, and I'll get time must be the distance over the rate. Okay, so let's work on that. So the first half, what's going to happen there? The first half, I've got 25 miles per hour, and I have to do this for half of 250, which is 125 miles. So for the first half, we're going to do 125 miles, that's the distance, and I'm going to divide it by the rate. Well, the rate was 25 miles per hour. If we figure that out, it comes out to be exactly 5 hours. All right, what about the second half? Let's do the same kind of thing. Second half, I want to have, it's again 125 miles. So 125, and then I want to divide by the speed. Now this speed was a little slower. This was 20 miles per hour. And if I figure that out, I did this ahead of time, it comes out to be 6.25 hours. So let's see, what's the total time this guy was flying on this day? Looks like he got finished a little early. If we add these up, it's a total time of 11.25 hours. All right, so 11.25 hours total. I have the total distance. It was 250 miles. So I'm going to form a fraction that will give me the speed now. And I just got to think about the units. This is miles per hour. So we went 250 miles, and we're going to divide this by how much time we spent. This is 11.25 hours. If you compute this out, it comes out to be about 22.2 miles per hour. That's not even exact. I had to round it off. But so the idea is here is the average speed actually came out not quite to be the halfway point of the other speeds, because it's related to how much time you spend total. And if you look what this bird was doing, it didn't actually spend the equal amounts of time at the two speeds. If it had, we would have gotten the speed halfway between. So this reminds me of an interesting old math problem I saw once. And what we're going to do is we're going to do a sample for our swallows, okay? So let's say, hypothetically again, let's say we had a swallow that was a little on the lazy side at the beginning. He was a slow poke. So let's say the swallow went the first half at only 10 miles per hour. So that means he's about half what the other guys were doing on average. So halfway through the day, or half the distance, he's way, way behind. So the question would be, for the second half, how fast should he go in order to get an average speed of 20 miles per hour? So the idea was, if he is really supposed to be going 20 miles per hour, but he is slow in the beginning, he's going half the speed, how long would it take, or how fast would he have to go to make up for that? You think, I went too slow, I'll just go faster later. Well, it's an interesting question, because if you figure it out, it turns out that the first time here, for him to go 10 miles an hour, just halfway, the 125 miles, he's going to spend 12 and a half hours doing it. He's used up all his time, and it's actually impossible for him to average 20 miles per hour for that day. Once he goes 10 miles an hour for too long, it's no good. You can't go a million miles an hour and make up for it. It's just too late. He cannot do it. So that bird, out of luck. Hopefully he keeps with the crowd, right? So anyway, a little math for our visitors here. An interesting thing about the swallows, they fly to San Juan Capistrano every year, the same ones, or the same group of them, and they hit the exact same spot, and they usually hit it on the exact same day. It's usually March 19th every year, give or take a day sometimes. How those birds do that, how they get to the exact same spot at the same time year after year, I don't know, and I don't think anyone else has figured it out yet either. I thought maybe we could talk a little bit about trick-or-treating, and in fact we have a trick-or-treater of our own here in the studio. We have 8-month-old Erin, and she is the daughter of our producer, Bill. There she is in her little chick outfit, all ready to go. So how are we going to work some math into this? Well, let's say that you want to do some trick-or-treating, and you know there's some key houses that you want to hit because they give the best candy. So for example, I have a little map printed out on my math cam here. Let's say you'd like to hit a couple houses, like maybe this one here. That finger keeps falling off, sorry about that. Let's say, I don't know, you want to hit this house, and this house, and this house. There's a mathematical way you can actually figure out the very best way to hit all these houses in what order. And if you think about it, there's actually quite a few different orders you could do. So I'm going to show you a technique, and it's kind of cool. It's really easy to understand. It's kind of a shame actually you don't see it earlier in a math class. But what we're going to do is I'm going to represent each house you want to hit by a dot on my math cam here, okay? So, for example, I'm going to put a dot on my paper, and this is going to represent your house. And let's say you want to hit 5 other houses. So I'm just going to represent each one by a dot, and I'm not really concerned about getting them accurate to the map. I don't care if this is in the right location or anything. All I want to do is list the 5 houses. I'll just call them A, B, C, D, E. And what I want you to think of is that we're going to connect the dots with a line if you can walk from one house to the other. And of course, you can walk from any house to any other house. So basically, from your home, I could go to any of these 5 houses first. And what we like to do is to figure out how long it would take you to do each of these walks. So you could say, okay, if I went to house A, how long would it take me? And, let's say it would take 5 minutes to walk to house A, and maybe 8 minutes to walk to house B, etc. And go through all the different options. And, from A, you could go to B and then C. And if you fill in all these different possibilities, you might end up with something a little like this. I did this ahead of time, so you have a nice picture for you. This is called a graph, and it's not a graph in the sense of the graphs you're used to. This is part of a field of math called graph theory. Computer scientists use this a lot, actually, and you'll see this a little later in your math career if you went past calculus. It's kind of a shame you don't see it earlier, though, because it's not hard to understand at all. I mean, the problems get complex, but it's not that hard to understand how the setup goes. So here I have a picture of your house and 5 houses, and we want to connect all of them. And I've written on here examples of how long it would take you to walk from house to house. Well, you can actually feed this into a computer, for instance, and it could tell you the very quickest way you could go. There's even some ways to do it by hand. For example, you could say, well, starting from your house, let's just go to the nearest, other house we can. So you look at all your options, and the closest one is, there's 8 minutes here, 15 here. Hey, there's one with only 4 minutes there. Let's go there first. So you might say, okay, let's go to the 4-minute house first. That's house C. Then you say, okay, which house should we go to next? Well, I've got an 8, a 7, a 2, and a 12. I don't want to go back home yet, so I'll take the 2 option. That means I would go to house A next. All right, what about after that? Well, I don't want to take the 8 route because that would take me back home. I'm not ready to go back home yet. I've got a 5-minute, 11, a 6. I think the 5 minutes is the shortest one. Let's go there. And okay, now I'm at house E. Where should we go next? Well, I've got a 10-minute route. I've got a 14-minute route. I'll take the 10-minute route. And then finally, I don't have many options left. I got to go to house B and then back home. So what you've done is you've done a complete loop through this diagram. It's called a circuit. And the idea is you've turned your problem into a problem of just connecting dots and trying to make a circuit through them. This is an example of a very famous problem called a traveling salesman problem. It's an unsolved problem in the sense that there is no surefire way to get the very best answer except for comparing all the possibilities. And unfortunately, there's a lot. You might think like, oh, there's only 5 houses to visit. How bad can it be? Well, there's over 100 different routes you could take to visit those 5 different houses and come back home. And what if there were, say, 10 houses? Well, then there's over 300,000 different combinations that you could do. That's a lot for you to check. So what they've done in recent times is fed these into a computer and have the computers crunch on them. I have an example to show you. I mean, just think about how huge these numbers get. This is a picture of all the cities of Sweden. I'll put it on my math cam for you. And someone made the most efficient route to connect all the cities. There's almost 25,000 cities in Sweden. They connected them all. You probably can't even see all these tiny red lines connecting every city to every other city in one huge loop. Well, it took the equivalent computing time of a single computer working for 80 years to figure this out. They have verified that this is the one, this is the best option. But it's a very difficult problem, and they're still working on it. Computer scientists love this problem. You might even see something like this if you went pretty far up in math classes. But as I mentioned, it's kind of a shame because it's not hard to understand the problem at all. It's not even hard to work on it by hand. It's just most math classes don't spend too much time on these types of things. They don't fit in the calculus class, I guess, but it's kind of cool stuff. So if we have a chance in another episode, I'll show you, Mathman Dan will show you some additional examples of how this comes into play. We actually are always watching current events to see if math shows up, and it turns out, of course, it does all over the place. But we like to mention it when it does happen. So this weekend, the largest U.S. bicycle race actually finished, the Amgen Tour of California. And lucky for us in San Diego County, it finished right nearby, actually, the last leg. And if you watch the news, they said there were about 300,000 spectators in the San Diego area this last leg. It actually started in Rancho Bernardo, went through Valley Center, and ended up in Escondido, which is practically right next door to us. So there's 300,000 spectators, and they estimated over 2 million spectators throughout the whole race. And it ranged from Northern California, Central California, and down here, Southern California. So this brings up the question, how do they know how many people are watching this race? Because it's not like they're counting them all. You don't have to have a ticket or anything. So this is a very sticky subject sometimes, actually, because there have been, believe it or not, arguments and fights over this, in fact, lawsuits, because some people staged protests and they claimed they had, 500,000 people there, and someone else said, like, no, you only had 200,000 people there, and then the police don't want to estimate crowds anymore. So it is a mathematical concept or a technique to do this, and it is not the easiest thing to do, but I was going to show you a general way that they actually do this. In fact, on my computer, I have a picture of a crowd at a bicycle race, and you can see, if you just saw a bunch of people like this, how would you possibly estimate how many there are? So we're going to actually do a little example here. This is a picture from National Geographic this is a crowd in India, and we're going to try and estimate how many people are in this particular snapshot, just in the part you can see on the screen. There's a lot of people there. You should go ahead and make a guess. This is like, guessing jelly beans in a jar. Those silly contests they have. I wonder what a belly jean is. I'll have to work on that. All right, so anyway, make a guess. How many people you think are in this picture? And we're going to show you how, at least some people, make a decently accurate estimate. It's still going to be a little loose estimate because there's just no way to be extremely accurate. But anyway, the idea is to actually draw a grid if you can get an aerial photo like this. So they might send a helicopter or an airplane over and try and get some good photos of a crowd if they really want a good estimate, and they're going to overlay a grid. So that's what I did. I drew a grid right on this picture here, and then you take one square. If they all look like roughly the same amount of people in each square, you pick a square, and you try as best as you can to count how many people are in one square on that grid. And I counted about 17 in the square I chose. So if I count 17 people per square, next I just have to count how many squares I have, and this is an 8 by 11 grid I drew, so there are 88 squares. I multiplied by 17 people in each square, and I got about 1,496 people. So there are about 1,500 people, at least in that picture, by my estimate, and that shouldn't be too bad, actually. Now, another recent event while we were on hiatus, of course, is Obama's inauguration, and I have a picture from there. And those crowds were huge. I mean, they were announced that they were over 2 million people. But I have a satellite photo, actually. And hold on, we have to zoom into this thing because this is pretty amazing here. That's a picture of the Washington, D.C. area. And you can't see much yet, I know. But there's the Washington Monument right in the middle of the screen. I'm going to zoom in on this. Hold on. The Washington Monument you see about, we'll get it right in the middle of the screen. You can kind of see it sticking up there. And there are, almost looks like a bee colony or something, but there are hordes of people around it. So let me get as close as I can. There's Washington Monument. See all those little specks? Those are people, and they were trying to estimate the crowd. So this is a legitimate way to do it. So there's the Washington Monument. Now watch. We're going to scroll towards the Capitol building or the White House, and here's the mall. All those are people. Eventually, we're going to get right up to the White House. You'll see. I can't remember if it's the White House or the Capitol building. More and more people. More and more people. Here we go. Finally, you're eventually going to see seating here, I promise. There's the lawn. Okay, there's the more formal seating area, and there finally is the building. So with a photo like this is just a satellite photo. They can actually make a pretty good estimate by doing similar techniques to we did. This would be a little tough. The crowd is so huge. Now, just for fun, I looked up some other techniques people used. One person has determined a sort of rule of thumb for general crowds. If you want to make an estimate and you have some measurements, like if you have the size of the stadium, or for example, if you're concert crowd or something, you know how big the field is. If you are at an arm's length distance from other people, it's going to be about 10 square feet per person that's going to take up. If you're in a pretty more tightly packed crowd, maybe not too uncomfortable, but fairly closely packed, it's going to be about 4.5 square feet per person. And if you're in a mosh pit, it's 2.5 feet per square feet per person. So that's like as tight as you can get. So they use those to help estimate too if they don't have the best photos. One last technique I thought was highly amusing, but is considered less accurate. They wait till the crowd leaves and they weigh all the trash that the crowd leaves behind. Because I guess there's some average amount of trash the crowd leaves behind. They can estimate how many people were there. It's kind of sad, right? Well, so let's not use that method. Let's use the aerial photography method. I like that better. Over the summer, we were actually doing some things out in the field, and we thought it'd be fun to drop a watermelon off the roof. Hey, why not, right? Well, there actually is some math involved, and we were particularly interested if we dropped a watermelon off the roof of our building, how far would the splat go? So there is some math involved. I'll show you that afterwards, but first, just check out the fun of what happened when we threw this guy off the roof. I'll show you the math afterwards. Check it out. That was me standing up there, but we actually did it twice just to see how it would go. And our watermelon, when we dropped it, the farthest piece flew 25 feet away from it where it landed. So it turns out there's not a simple equation I can show you that'll tell you how far it's going to splat, because there's a lot of different things that go and get involved in that. But there are some things we can figure out. In fact, there's a few concepts we can borrow from physics. And one of the main ideas we have is that when I trucked this watermelon up to the roof, I was basically giving that watermelon potential energy. And when I drop it, that energy gets translated to kinetic energy when it hits the ground. And there's a formula that tells you how much kinetic energy that will have when it splats. So on my math cam, I have a little formula written down, borrowed from physics. This is, the M here you see is for mass. So it's basically, you can think of that as the weight of the watermelon. And the V is velocity. So if you look at this, the energy just depends on two things. It's how much mass you have when you're watermelon, and it's the square of the velocity. So that's important to notice, because that means if you speed the watermelon up, you are actually squaring that as far as how that contributes to the amount of energy it's going to have when it hits. So if you, for example, if you make the velocity double, you don't double the energy, you actually quadruple the energy because it's related to the velocity squared. So really all we need to know is how fast this thing was going and how much it weighed. And there's another formula from physics we can use that'll determine exactly how fast it was going when it hit, and all I have to do is know how far up I took it. So I'll show you that formula. This is, if you start from rest, meaning you don't actually throw it down, that's what I did, I just leaned over the edge and dropped it, then the velocity you end up with is going to be 2 times A is acceleration, in this case that's purely from gravity, and D is the displacement, which is simply the height above the ground that I dropped it at. Well, I measured the height when we were there, and we measured up the side of the building. So I can actually tell you what these values are, and A, in fact, this is the gravity, and if you're measuring in feet, this is 32 feet per second squared. They figured that out a long time ago. The displacement, we were 23.3 feet up, and I multiply that by 2, and that will give me a value for my velocity squared. So I did this ahead of time. This came out to be 1491.2. And you can even watch the units. The units will work out. If you ever take any sort of science class like chemistry or physics, they will hound you relentlessly about making sure you have the units there. So we'll be good here and we'll include them. I have feet times feet, so I'll write feet squared, and I have seconds squared. So if I take square roots, since this is the velocity squared, we can figure out that the actual velocity of my watermelon, it comes out to be about 38.6, and the units would be feet per second. So I converted that to miles per hour. It came out to about 26 miles an hour. That might not seem that fast, but the thing is we weren't that high up. This is only a 2-story building that I was standing on top of. So if you want to compare this, every year UCSD has a watermelon drop at the end of the school year, every June, and they actually have the students vote for the watermelon queen, and she climbs up to the 7th floor of a building and she drops the watermelon. And it varies every year because, like I said, there's more that goes into the splatting than just how much energy. But the record was in 1974, and a piece went 167 feet. Now that's obviously her watermelon's going a lot faster than ours because it was several feet up, several stories up. I estimate hers was probably going between 70 and 80 miles an hour. And it turns out actually the fastest a watermelon's going to go, the terminal velocity they call it, is about 112 miles an hour. In theory, they would keep accelerating, but the wind resistance finally starts slowing them down, and they kind of hit a maximum. So in our little equations, we were ignoring the air resistance, but I think it's pretty safe because we didn't drop ours very far. So anyway, if you're careful, you can go on your roof and drop some watermelons and see what happens. Just be careful to clean it up afterwards, of course. We did. We were very good citizens. So just for a little fun, a little math for you there from the so-called real world.